Imagine spending nearly half of your workweek just cleaning and preparing data before you can even start building an AI model. In clinical research, this data preparation bottleneck is incredibly severe, especially for complex conditions like heart failure. Today, we are looking at a breakthrough system called nMAS, or the Nimblemind Multi-Agent System. It automates the tedious process of clinical feature engineering, turning messy electronic health records into clean, structured, and highly predictive features while keeping every single data point fully auditable. To understand why this is such a massive challenge, we have to look at how heart failure is diagnosed and tracked. Clinical definitions rely on a complex mix of lab results, medication histories, comorbidities, and imaging data like ejection fraction. Currently, data scientists have to manually write rules to reconcile these fragmented, longitudinal records across multiple database tables. This manual process is not only slow and expensive, but it also lacks a standardized way to trace a derived feature back to its original clinical evidence. This is where the Nimblemind Multi-Agent System, or nMAS, comes in. Instead of relying on unstructured summaries or brittle manual code, nMAS introduces a structured, two-stage pipeline. First, it standardizes, deduplicates, and aggregates raw EHR tables at the patient level. Second, it applies a clinical scoring rubric to generate higher-order composite features. Crucially, a restricted language model acts as an auditor to validate these features, ensuring that every generated variable is structurally sound and directly linked to its clinical source. Let's dive into how nMAS actually calculates these features using a clinical scoring rubric. Developed alongside clinical guidelines and reviewed by a professional cardiologist, this rubric assigns points to different clinical indicators. For instance, in assessing disease severity, a severely reduced ejection fraction midpoint yields 35 points, while elevated biomarkers like BNP add up to 20 points. By summing these points and mapping them to ordinal categories, nMAS translates complex, multi-domain clinical data into interpretable risk and severity scores. To test the real-world utility of these engineered features, the researchers trained XGBoost classifiers on two critical heart failure phenotyping tasks. When they added the nMAS composite features to the baseline variables, the results were outstanding. For classifying heart failure with reduced ejection fraction, the model's area under the AUROC curve jumped from 0.895 to an impressive 0.963. We saw a similar, significant boost for preserved ejection fraction phenotyping, proving that these structured features capture deep clinical signals that raw variables miss. Beyond raw predictive power, the researchers wanted to ensure these features were truly meaningful. Using SHP analysis, they discovered that the nMAS composite features, like demographic vulnerability and disease severity-adjusted gaps, were actually the most influential predictors in the models. Furthermore, an independent evaluation using Claude Opus scored the engineered features at over 81% for methodological soundness and external evidence support. This confirms that the automated pipeline isn't just finding random correlations, it's engineering clinically valid features. While these results are highly promising, the authors point out several key limitations. First, this pilot study was evaluated on a cohort of 500 dummy patient records from a single institution, meaning we still need external validation on larger, multi-institutional datasets. Additionally, some comorbidity and behavioral features rely on regular expression matching, which might miss atypical clinical language. Finally, because some features incorporate phenotype-related evidence, there is a potential for feature label overlap that requires careful handling in future designs. Looking ahead, the implications of this research extend far beyond heart failure. The core design of nMAS separates clinical knowledge representation from feature execution. This means any data-intensive chronic disease, from diabetes to chronic kidney disease, could substitute its own clinical rubric into this scoring engine without rebuilding the underlying pipeline. By automating and auditing clinical data preparation, nMAS paves the way for faster, more reliable, and highly reproducible clinical AI research.